Hi there, welcome back. We mentioned that the choice of coordinates is a key part for successfully solving problems. Let's see then a couple of examples. When describing the position of a point particle on a plane, we need two numbers, two coordinates, which in Cartesian coordinates they are x and y. These in polar coordinates can be described with r and theta, being r the distance to the origin of coordinates and theta the angle it subtends in the counterclockwise direction. We can write one set of coordinates in terms of the other. X is equal to r times cosine of theta and y is equal to r times sine of theta. In Cartesian coordinates we have the unit vector x hat and y hat. In polar coordinates we have r hat and theta hat. In the former case, x hat and y hat do not change, they do not depend on the position of the point particle, but in polar coordinates they do change. The unit vectors are position dependent. If we look at this drawing, we see that the radial unit vector at this arbitrary position is given by r hat equal to cosine of theta x hat plus sine of theta y hat, and r hat is equal to minus sine of theta x hat plus cosine of theta y hat. These two unit vectors are orthogonal, just as x hat and y hat. With this in hand, I want to write Newton's law in polar coordinates. At the end of the day, remember that that's the way we know to solve mechanics problems so far. It's by writing forces and using Newton's second law. So I need to know how Newton's second law looks like in these coordinates. To do so, I'm going to find the acceleration in polar coordinates. So first, I'll derive and find the velocity, and derive again to find the acceleration. Taking the time derivative of r hat and theta hat, we get equal to minus sine of theta, theta dot x hat plus cosine of theta, theta dot y hat, and theta hat dot equal to minus cosine of theta, theta dot x hat minus sine of theta, theta dot y hat. If we compare the two equations with the definitions of r hat and theta hat in terms of x hat and y hat, we see that r dot hat is equal to theta dot theta hat, and theta hat dot is equal to minus theta dot r hat. These equations describe the velocity in polar coordinates. The change of both unit vectors depends on the rate of change in the tangential direction, but not in the radial direction. This makes sense. If there was only radial motion, the orientation of these unit vectors would not change. We can write this in one single expression for the velocity in polar coordinates. Now, let's derive this again to find the acceleration. If we group the terms with r hat and theta hat, we finally get this is the acceleration written in polar coordinates. Now, we can go back to our old friend Newton and write that F is equal to F sub r, r hat, plus F sub theta, theta hat. So F sub r is m times r 2 dots minus r theta for square, and F sub theta is m times r theta 2 dots plus 2 r dot theta dot We have the radial force and the tangential force here. The first term of each force are intuitive, just the rate of change of those directions. The second term of F sub r is another old friend, the centripetal force proportional to the square of the velocity. The last term in the tangential force is not that intuitive. This is Coriolis force. This term comes as a consequence of being on a reference frame that rotates with respect to an inertial frame. Remember that the polar coordinates are rotating. Let's look at an example. Consider a pendulum of a string of length L and a bob of mass m, undergoing circular oscillations. The pendulum subtends always an angle alpha with respect to the vertical, and the bob moves on its horizontal plane. Because of the circular motion, the radius is constant, r equals to L sine of alpha. Let's find the frequency of the motion. To do that, we will write Newton's second law. The bob moves on a circle, so there is a horizontal radial force. F sub r equals to mr theta dot squared, where r is L sine of alpha. Vertically, there is no acceleration, and the balance of forces is due to the vertical component of the tension, T cosine of alpha, and the weight mg of the bob. We can solve these two equations to find that the angular velocity omega is the square root of g over L cosine of alpha. If alpha is close to 90 degrees, the angular frequency tends to infinity, as it would have to be moving very, very fast to keep that angle. If alpha is close to 0, the cosine of 0 is 1, and we will recover the frequency of a simple pendulum.